Okay, so welcome to this video. In this one, we're going to look at, if you remember the last video, we looked at the bit that's underlined in red here, looking at when kinetic energy of the particles increases. This time we're looking at the green bit, so when the potential energy of the particles increases. So in terms of our graph, okay, we're looking at the changes of state here. I'm going to talk about the amount of energy needed for something to change state. And again, if we go back to our statements about what happens when you heat up an object, it's this bit here about changing the state of the object. Okay, so like I said, then we're focusing here on an object changing state. And so the title for the concept that we're going to need here is specific latent heat. Now, what does that actually mean? Well, like I said, then when you're heating up a substance, you're putting energy into it, there'll come a point where it changes state from, say, a solid into a liquid. And in order to change something's state, you're going to have to weaken or break the intermolecular bonds, the bonds or forces holding those particles together. And so the energy that you actually need in order to do that, to change the object state, is called latent heat. So latent heat just means the energy needed to change the state of a substance. Let's write that down. Okay, so latent heat, that is the energy that you actually need to put in order to change the state. And so like we said before, if you are putting energy in, you're increasing the internal energy of the substance still, but this time it's not the kinetic energy of the particles that's increasing, so the temperature isn't going up, but it's the potential energy of the particles that's going up because you are breaking or weakening those bonds. Similarly, when a substance cools down and changes state, for example, from a liquid into a solid, energy is released because bonds are being formed, and that's also called here the latent heat. Now let's think about what things will actually affect the energy needed. Well, there's two things that's going to affect the energy that you need to change the state of a substance. Okay, so factors affecting the latent heat or the energy needed. Well, there's two things. There's the mass and there's what the substance actually is, or I suppose you could say the material. Because different substances, you're going to require different amounts of energy in order to change their state. And so just like with specific heat capacity, we have a property of a material or a property of a substance which determines this, and it's called the specific latent heat. So let's have a look then at what that actually means. Okay, so let's go with our definition then for specific latent heat. It's quite similar in a way to what we have for specific heat capacity. Okay, so specific latent heat is the amount of energy required, and I guess it's really this word specific. We said a minute ago that the amount of energy in general is just called the latent heat. So the specific latent heat is just the amount of energy required to change the state of just 1 kilogram. Okay, and actually that word specific in terms of physics and science does mean per kilogram. So to change the state of 1 kilogram of a substance. And that value, specific latent heat, is going to be different for different substances, for different materials. And in fact, it can also be different for the different changes of state. So for example, it takes a different amount of energy to change 1 kilogram of ice into water than it does to change 1 kilogram of water into steam. And so actually there are a couple more key words that we need to know about here. And it's to do with the different transitions. So you can have what's called the specific latent heat of fusion. Okay, and the specific latent heat of fusion, okay, that's relating to the solid to liquid state change. Okay, and then you can also have what we call the specific latent heat of vaporization, and that is when we're referring to the liquid to gas state change. Okay, that hopefully will become a bit more clear in a second when we look at some examples. Okay, right, let's have a check of the formula then. It's formula time. Well, you might actually be able to work it out from this. It's not too tricky. Specific latent heat is the amount of energy required to change the state of 1 kilogram of a substance. Now, the way you do normally see it written is slightly rearranged, so I'm going to rearrange it slightly. I will write it on exactly as it appears on the formula sheet. And again, this one does appear on the formula sheet. So I should be able to fit it in down here. So what we've got then, we're looking for the amount of energy. So the thermal energy for a change of state. So in other words, how much energy do you need to change the state of an object? Equals the mass of the object times the specific latent heat. Okay, now we can look at the units, and hopefully you already know that energy is in joules and mass is in kilograms, and so it shouldn't really come as a surprise that specific latent heat, if it's the energy required per kilogram, is measured in joules per kilogram. And if you do want it in symbols, actually, again, it's quite a logical one and is on the formula sheet, so feel free to do this one in symbols. E for energy equals small m for mass times capital L then for specific latent heat, obviously the L standing for latent. All right, let's have a look then at a couple of examples. Okay, here's an example then. So 54.3 kilojoules of energy are released when some helium is condensed. Obviously, we're looking very, very low temperature here. Helium, as you know, is a gas at room temperature. In fact, its boiling point, so the point where this must be happening, is minus 269 roughly degrees C. So very, very cold. Anyway, 54.3 kilojoules of energy are released when some helium is condensed. What mass of helium is used? Obviously, question mark there. And it tells us here the specific latent heat of vaporization of helium, because if we're talking about condensing, we're going gas to liquid, so we want specific latent heat of vaporization, not of fusion. Obviously, it would always give you that data in the exam. You're not expected to remember the specific latent heat of vaporization of materials. So, first step, as always, write the formula. And I'm going to do it in symbols simply because it is one that's given to you on the formula sheet, so it's not going to be a massive issue. Energy is mass times specific latent heat. Okay, energy, 54.3 kilojoules. Well, usual thing. Okay, we've got to convert that. So that's multiplied by 1,000 gives us 54,300 joules equals mass times. I've done this on purpose. You can see here this written in standard form now. Most of you will be familiar with standard form. If not, you will do it in maths at some point. You can either write it down like that. That's probably the way I'd recommend doing it, to be honest. Or obviously, if you'd rather actually work out what that is as a normal number, feel free. So what I need to do then, to find the mass, divide both sides by this. So the mass is going to be 54,300 divided by 2.09 times 10 to the 4. And I might just take this opportunity to show you that you can do standard form on your calculator. A lot of you may not know this. Now, I know there's lots of different designs of calculator out there. However, if you look at sort of a standard scientific calculator here, I've just messed up that focus a bit, but never mind. This button at the bottom that says times 10x is a standard form button. So if I want to do this calculation, okay, I know you can't see that super clearly. Okay, I've got 54,300, and notice how I'm doing it in the sort of fraction mode, okay, divided by, and then 2.09 times 10 to the 4, I just type in 2.09, then the times 10x button, and then 4. And it gives me an answer then of 2.6. So my answer then is 2.6 kilograms of helium. Okay, so hopefully that makes sense. Right, what I want to do then, just as a final example, is do one more which brings in actually something from the last video as well, just to tie all this together. Right, okay, so this on surface looks quite a simple question. Find the energy required to change 200 grams of ice at 0 degrees C into steam. Actually, though, that's a bit of a beast of a question, because if we think about it, there are various different parts to this. First thing, actually, I'm going to do just before we do anything else to make sure we've noticed is this 200 grams, as we know, needs to be in kilograms. So let's do that straight away. Divide by 1,000, 0.2 kilograms. Now let's think about it. So we've got ice at 0 degrees C. We want to turn that into steam. We first of all got to turn that ice into water. Okay, so the first thing we've got to do is think about how much energy we need to turn 200 grams of ice into water. Then we've got to heat that water up from 0 degrees C. Well, if it's steam, it must be up at 100 degrees C, so all the way up to 100 degrees C. And then we've got to change the 200 grams of water into steam. Now remember, the mass is not going to change. If you've got 200 grams of ice, when it melts, it will be 200 grams of water. Similarly, when it then turns into steam, that will be 200 grams of steam. So mass is conserved in any change of state. But we've got three separate calculations to do here. So let's go through this logically. Okay, step one, this is for turning the ice into water. So if it's a change of state, we go to our formula from this video. Okay, energy is mass times specific latent heat. Okay, specific latent heat, mass 0.2 times specific latent heat. Now obviously this is the ice into water state change. Therefore we want specific latent heat of fusion. So green, by the way, is my sort of data bank here. So I go specific latent heat of fusion. There it is, 334 kilojoules per kilogram. So that's 334,000, or you could write it 334 and then times 10 to the power of 3. That's another way they can write big numbers, obviously using the K for kilo. Okay, so we've got 0.2 times 334,000. I'll put that into my calculator. And I get an answer of 66,800. So I need 66,800 joules just to turn 200 grams of ice into water. That's quite a lot, really. Anyway, moving on. Number two, we've now got to increase the temperature of the water that we've just got here from 0 all the way up to 100. So if it's the amount of energy to raise the temperature of a substance, we go to our formula from last time. So this is where we need our specific heat capacity formula. So delta E equals mass times specific heat capacity times, remember, delta theta for change in temperature. Okay, well, we are looking for the energy again. Mass is 0.2. Right, specific heat capacity then of water, you can see that's at the bottom here, is just 4,200. Delta theta then, the change in temperature, well, from 0 up to 100 is obviously 100. Okay, so if I put that into my calculator, I get an answer of 84,000 joules. And then finally, okay, I then need to work out the amount of energy that I need to change the state of all the water into steam. So it's the formula from today again, E equals M times L. Okay, I'll just about have enough room to squeeze that in. So the mass is 0.2. Now this time, because we're looking at the water into steam, we want the specific latent heat of vaporization, which is actually higher, quite a lot higher than the specific latent heat of fusion. That's 2,260, but it's times 1,000. It's actually 2,260,000 joules per kilogram is the specific latent heat of vaporization of water. And so if I work that out, 260, I get 452,000. So it takes 452,000 joules to turn 200 grams of water into steam. And so therefore, if I want the total energy required, I'm just going to add all these up. So 66,800 plus 84,000 plus 452,000. And it gives me a grand total of 602,800 joules. So that's how much energy you would need if you wanted to get 200 grams of ice and heat it all the way up so it turns into steam. If you can understand that question, okay, you've pretty much got the concept of this topic. Right, well, I hope that's been useful. That's actually the final video in this little section, so I'll speak to you all again soon.